Ready to dive into a world that's incredibly familiar and surprisingly strange at the same time.
I'm ready when you are.
Okay, then. Let's take a deep dive into, well, numbers.
Numbers, seems
Uh,
simple enough.
yeah, we use them every single day, right? But have you ever really stopped and, thought about it? I mean, the whole concept is kind of wild, right?
It really is when you put it like that. I mean, these symbols we use to represent quantities,
Real.
relationships.
Exactly. It's pretty mind-blowing, if you ask me. And that's what we're going to be exploring today.
Sounds like a plan. Where are we starting this exploration?
Well, we're going to be diving deep into a fascinating book by Tobias Danzig called Number, the Language of Science. It really takes us on a journey through the whole evolution of how humans came to understand this really abstract concept.
Sounds right up my alley. I know a little bit about Danzig. He's got some pretty interesting ideas about how different cultures develop their own unique ways of counting.
Right, like he talks about the Tsimshian language.
Ah, yeah. The Tsimshian, their tribe up in British Columbia, I think.
That's the one. And their number system, man. Pretty wild stuff. Danzig says they have 7 sets of number words.
7 sets. Wow. That's incredible. You mean they didn't just have one concept of, say, 5, like we do?
Nope, they had all these different words for counting different things.
Like what kind of things?
Well, let me see if I can remember. They had different words for, flat objects, round objects, people, trees, canoes, you name it. I mean, their whole system of numbers was tied to the actual world around them. Pretty
So it
cool.
really highlights how deeply rooted numbers are in our, human experience. It's not just some abstract concept floating out there. It's tied to how we interact with the world, how we make sense of things.
Totally. But at some point, we had to move beyond just those concrete, meanings. Develop more abstract systems that could handle bigger numbers, more complex calculations.
Exactly. We needed a system that could go beyond just counting the things we could see and touch.
And even in English, like today, we see these little hints of that concrete past.
Give me an example.
Okay, well, think about words like pair, couple, brace. I mean, they all represent the number 2, but they're used in such specific contexts, right?
Yeah, you're right. It's like those specific meanings, well, they faded over time. And that abstract concept of just two, it emerged from all those specific uses. Pretty fascinating, I think.
It is. Okay, so speaking of abstract systems, the one we use every day, the decimal system, base 10. I've always wondered, is that just a coincidence? The fact that it matches, the number of fingers we have?
Danzig calls it a physiological accident. Kind of makes you wonder, right? What if we had evolved with 8 fingers or 12?
Would we be doing math in a totally different way?
Maybe, and some mathematicians actually argue that base 10 isn't even the most efficient base.
What, they think we should be using something else?
Yeah, some people are really into base 12, for example.
Base 12. What's so great about that?
Well, think about it. It divides really easily into halves, thirds, and quarters.
Oh, yeah. Makes sense.
Imagine how much simpler fractions would be if we had 12 as our base.
Okay, yeah, I see what you mean. I'm trying to picture a clock with 12, no wait, with how many hours? And rulers based on 12. Man, that's weird.
Right. It's a real mind bender to try and imagine a world with a different number base.
It's making my brain hurt just thinking about it.
Yeah.
So, even prime numbers, right? They've been suggested as a base for a number system. Lagrange, that guy, the mathematician,
Oh, yeah,
he
Lagrange.
was all about using prime numbers as a base.
He loved the idea that in a prime base, every single fraction would be unique and irreducible.
No more arguments about 1/2 versus 3/6.
Exactly. But whether we like it or not, we're pretty much stuck with our decimal system. And Danzig actually talks about how, getting it adopted, that was quite a battle.
Really, like a war over numbers.
Well, not literally a war, but Danzig describes this real struggle between what he calls the abacists.
The abacists?
Yeah, they were totally attached to their counting boards, right? Super
Yeah.
old school.
Yeah.
But then you had the algorists.
Algorists. I see where this is going.
Yeah, they were all about this new system, the Hindu-Arabic system with its revolutionary concept, zero.
0. Okay, let's talk about 0. I mean, it seems so basic to us now, but it was a total game changer, right?
Oh, absolutely. It's hard to even, imagine doing math without it. I mean, it's mind-boggling. Zero allowed us to finally express nothingness as an actual number. Think about it, that's huge.
Then you put it that way.
It's what made positional numeration possible and opened the door to algebra and basically everything that followed.
Danzig calls it a world event. which might sound a bit dramatic, but
No, I get it. When you think about the impact it had, it's pretty wild.
it's fascinating, right? How such a simple concept, just this one symbol, had such a profound impact on math, on science, on our whole understanding of the world. And, Danzig doesn't stop there. He goes on to talk about number theory, too.
Ah, number theory. Sounds kind of intimidating, doesn't it?
Yeah, a little bit. To be honest, I've always been kind of intimidated by it. Like, what even is number theory?
Don't worry, it's not as scary as it sounds. Really, at its core, number theory is the study of integers,
Yeah.
just whole numbers. And it goes way back. Like, ancient cultures were totally fascinated by the relationships between different numbers.
So it's not just about, like, practical calculations and stuff. There's a philosophical side to it, too.
Absolutely. Think about the Pythagoreans, for example. They were, like, obsessed with numbers.
Oh, yeah, those guys. They believed numbers held the key to, like, the entire universe, right?
Right. They saw divine significance in all sorts of numbers and numerical patterns. They even had this whole thing with those, what were they called? Amicable numbers?
Amicable number. Wait, are those the ones where, like, the sum of each number's divisors equals the other number?
You got it. That's amicable numbers for you. They were also super into perfect numbers. Those are numbers that equal the sum of their own divisors.
Okay, yeah, I vaguely remember that. I think 6 and 28 are the smallest ones, right?
You got it. Those were actually known even to, like, the ancient Hindus. Pretty cool, huh?
I'm starting to see the appeal of all these, like, numerical patterns and stuff. But I also seem to remember reading that, these explorations. They led to some pretty unsettling discoveries, too, things that kind of messed with the whole Pythagorean worldview.
You're talking about irrational numbers.
Yeah, the irrational numbers. It must have been a real shock to the system for them to find out that there were these numbers that couldn't be expressed as simple fractions.
It was a major crisis in the history of mathematics. It challenged everything they thought they knew about numbers.
And to think, it all started with something as simple as, like, a square.
Exactly. Imagine a square with sides of length 1. You've got your trusty Pythagorean theorem ready to go, right?
Of course. But where's this going?
Just try to measure its diagonal.
Okay, so I measure the diagonal, and
Oh, you'd think it would be a straightforward ratio, wouldn't you? Like maybe 2 to 1, something nice and neat.
yeah, that's what I'd assume. What's the catch?
That's exactly what the Pythagoreans thought, too. But using their own theorem, they managed to prove that the length of that diagonal, it couldn't be expressed as a fraction at all.
Whoa. Really? At all?
Not at all. It's what we now call the square root of 2, our first encounter with an irrational number.
So, like, no matter how hard they tried, they couldn't write it down precisely.
Nope. They could get close with fractions, but they could never perfectly capture it. It's like it just kept going and going forever. Danzig actually explains how they proved this using this very clever argument called proof by contradiction.
Proof by contradiction. I feel like I've heard that term somewhere.
Yeah, it's a classic. Basically, you start by assuming the opposite of what you're trying to prove.
So in this case, you'd assume that the square root of 2 can be expressed as a fraction.
Right, but not just any fraction. It has to be in its simplest form. Then you go through a series of, like, totally logical steps, and boom, you end up with a contradiction.
Okay, I'm starting to remember this now. So if you end up with a contradiction, that means...
It means your initial assumption must be false. So the square root of 2 cannot be a fraction. Case closed.
It's like a mathematical puzzle, where the pieces, they just refuse to fit together. Pretty cool, huh?
It is cool. And you know what's even cooler? This whole thing, it just opened up this massive new world of numbers beyond what we could easily express or understand. Like, it blew the doors wide open.
So it wasn't just irrational numbers that were, like, challenging the ancient view of mathematics.
Right.
I mean, there were other things, too.
Oh, yeah, for sure. Danzig also talks about Zeno's paradoxes. Have you heard of those?
Oh, yeah, Zeno.
Yeah.
Those always mess with my head. Weren't they, like, all about motion and infinity?
Yep. Mind-bending thought experiments about, like, the very nature of space and time.
They're so trippy. Can you remind me of one of them?
Sure. Okay, so one of the most famous ones is the story of Achilles and the tortoise. So you've got Achilles, the fastest runner ever.
Of course, Achilles.
Yeah.
Everyone knows Achilles.
Okay. Right, so he's racing a tortoise. But he gives the tortoise, like, a head start. What Zeno argues is that Achilles can never actually overtake the tortoise, because by the time he reaches where the tortoise started, well, the tortoise has already moved a little further ahead.
Right, right. And then, like, Every time Achilles catches up to where the tortoise was, the tortoise is just a little bit further ahead.
Exactly. It's this whole infinite regression thing. It gets you thinking about, like, can you ever truly reach your destination if you just keep dividing the distance into smaller and smaller segments?
Those paradoxes must really stumped people back in the day.
They did. For centuries, philosophers and mathematicians were trying to wrap their heads around it. Like, how do you reconcile this concept of infinite divisibility with the fact that, well, we experience the world as finite beings? We get places.
So did we ever figure out a way to tame infinity, like mathematically speaking?
Over time, we did develop tools and concepts that helped us grapple with it, like the idea of limits.
Limits. I vaguely remember those from calculus class.
Yeah. Limits let us approach infinity, but without ever actually getting there. And then there's calculus itself.
Oh yeah, calculus. That was a fun class.
Calculus revolutionized mathematics, and it relies heavily on infinity. Like, it deals with infinite series and these infinitesimal quantities.
So we found ways to work with something that we can never really fully grasp. That's pretty amazing when you think about it.
It is. So how do you think all this impacted, like, our understanding of the number system as a whole?
Well, it led us to what we now call the realm of real numbers.
Real numbers. Sounds important.
It is. It's this like massive expansion of the number line that we all know and love.
Okay, take me back to the beginning. Where did we start with numbers?
We started with the simplest ones, right? The natural numbers, 1, 2, 3, and so on.
Simple enough. What next?
Then we added 0, right? That was a big deal. Then came fractions, negative numbers.
And all of those fit pretty neatly onto a number line. But what about those pesky irrationals? Where do they fit in? And how do you even, like, define them rigorously?
Good question. I mean, they don't really fit neatly into the whole fraction thing.
Danzig explains how mathematicians came up with some pretty clever ways to define those unspeakable numbers. Like, there's this thing called Dedekind cuts. Have you heard of those?
Dedekind cuts. I'm not sure. Sounds a bit like butcher shop terminology.
Kind of. Right. Okay, so imagine you're cutting a line into two parts. That's basically what a Dedekind cut is. It defines a number by how it divides all the rational numbers into those two sets.
So instead of defining a point by its like numerical value, you're defining it by where it creates a boundary.
Exactly. It's a bit more abstract, I know, but it lets us include those irrationals into the system. It gives them a place to live on the number line, even if we can't write them down as a nice, neat fraction.
It's fascinating, right, how we keep having to like reinvent our concept of numbers as we learn more about them. But isn't the idea of a cut still kind of reliant on geometry? Like, I thought we were moving away from visual intuition and toward a more abstract, like, system of logic.
It's true that Dedekind used a visual analogy to explain his idea. But at its core, the concept of a cut, it's really about logic, not about physical space.
Okay, I see. So what did Dedekind's work actually achieve?
Well, it helped mathematicians construct what we call the arithmetic continuum.
The arithmetic continuum.
Yeah.
Okay, that sounds pretty grandiose.
It is. Think of it as a complete and unbroken number line, one that includes all real numbers, the rationals and the irrationals. No gaps, no holes.
So we filled in all the gaps on the number line, huh? But knowing how this story usually goes, I have a feeling that's not the end of the story.
You know it. And those irrationals, well, they were just the beginning. Buckle up, because things are about to get even weirder when we start talking about complex numbers.
Complex numbers, huh? Those are the ones with the square root of -1, right?
Yeah.
The infamous imaginary numbers.
The one and only. But Danzig makes this really interesting point. What starts as a mathematical fiction often ends up having some very real applications.
Okay, I'm intrigued. Tell me more about these complex numbers.
Well, it all started with the need to solve equations that didn't have any real number solutions.
What do you mean? Give me an example.
Sure. Take the equation x squared plus 1 equals 0.
Okay, x squared plus 1 equals 0. Let me think about that for a second. I can already see where this is going.
What do you mean?
Well, I'm thinking there's no real number that you can square and then add 1 to it and get 0 as a result.
Right. Because any real number, when you square it, is going to be positive.
Exactly. So you're telling me mathematicians just invented a new number to make the equation work?
Pretty much. They said, okay, let's introduce this new number. We'll call it the square root of -1, and we'll represent it with the letter I.
Wait, hold on. How do you just, like, introduce something so imaginary into a system that's supposed to be based on logic and reason? That must cause quite a stir, right?
Oh, it did. There were plenty of mathematicians who were super skeptical about these complex numbers. They thought it was all a bit too, well, imaginary.
But how did they eventually become accepted? I mean, they are a pretty fundamental part of math these days.
Well, mathematicians were able to show that these complex numbers, combinations of real numbers and multiples of I, they could actually be manipulated just like regular numbers. You could add them, subtract them, multiply and divide them.
So they basically expanded the number system to accommodate these new
Oh,
entities.
exactly. They figured out the rules of the game for complex numbers, and it turned out they played by all the same rules as the real numbers. They were consistent, they were logical.
Okay, so they had the logic down. But how do they make them more palatable to the skeptics? I mean, it's still pretty hard to wrap your head around the idea of the square root of -1.
Well, they came up with a pretty ingenious way to visualize them.
Okay, tell me you're about to mention the Argand plane, because that's ringing a very distant bell from, like, high school math class.
You got it. The Argand plane to the rescue. It's basically a two-dimensional plane where you represent complex numbers as points.
Like a graph.
Exactly. The horizontal axis represents the real part of the number, and the vertical axis represents the imaginary part.
So you're not plotting, like, X and Y coordinates. You're plotting the real and imaginary components of a complex number.
You got it. And this, like, geometric interpretation was huge. It made complex numbers way more legitimate. It showed that they weren't just some, like, abstract symbols floating around in the ether. They had a visual counterpart. You could see them. You could work with them geometrically.
And of course, the really mind-blowing part is that this thing that started as a way to solve certain equations turned out to have these incredible applications in all sorts of fields.
It's true. Complex numbers are now absolutely fundamental to physics, engineering,
Yeah.
signal processing, you name it.
It's amazing, right? It all goes back to this basic question, like, what even is a number? Where are the boundaries? And as Danzig points out, those boundaries, well, they're constantly being pushed outwards. We're always discovering new and weirder things about numbers. It's a journey that takes us to some pretty wild places, like the realm of infinity. And even with all our fancy math tools and concepts, infinity, I mean, it still remains this, like, super challenging concept to wrap our heads around.
It's true. And Danzig, he talks about the work of Georg Cantor, who really shook things up in the world of math by developing a way to actually compare the power of different infinite sets.
Wait, you're telling me some infinities are bigger than others? That sounds like a paradox.
I know, right? It's totally counterintuitive.
Oh, yeah.
But Cantor actually proved that the set of all natural numbers, like 1, 2, 3, and so on, that set is smaller than the set of all real numbers.
Hold on. How can one infinity be smaller than another? They're both infinite.
I know. It seems crazy. But it comes down to how we match up elements between sets. For finite sets, we just count them, right? Easy peasy. But for infinite sets, we have to use this idea of one-to-one correspondence.
One-to-one correspondence. I'm not sure I follow.
Okay, so if you can pair up every single element in one set with a unique element in another set, then we say those two sets have the same size, or what we call cardinality.
Okay, that makes sense. But what if you can't make those pairings?
Then things get interesting. Because if you can't create a one-to-one correspondence between two sets, then it means one set is bigger than the other.
Even if they're both infinite.
Even then. And Cantor was able to prove that you cannot create a one-to-one correspondence between the natural numbers and the real numbers. There will always be real numbers left over, so to speak. It's like trying to squeeze all the sand on a beach into a thimble.
Wow, that's mind-blowing. So there are, like, levels of infinity. Did this change how we think about the number line?
It did. It opened up a whole new area of math called transfinite arithmetic. But be warned, dealing with infinity can get very, very tricky.
I bet. Didn't somebody even come up with a paradox related to infinity?
You bet they did. There are a few, but one of the most famous is Russell's paradox. It deals with sets that contain themselves.
A set containing itself. Okay, now I'm really confused.
Yeah, it's a tough one. Think about the set of all things that are not apples.
Okay, all things that are not apples.
Well, that set would actually contain itself because the set itself, it's not an apple.
Okay, I think I get that.
Right.
So what's the paradox?
The paradox comes in when you consider the set of all sets that do not contain themselves.
Okay, so now the question is, does that set contain itself?
Exactly. If it does, then it shouldn't be in the set. But if it doesn't, then it should be in the set. It creates this crazy contradictory loop.
Man, that's a real head-scratcher. It makes you realize that even our most basic concepts like sets and numbers can lead to these incredibly complex questions. So how did the math world react to Cantor's work?
Oh, let's just say it caused a lot of controversy.
Like what?
Well, some mathematicians, like Kronecker, they were totally opposed to Cantor's ideas about infinity. They thought it was all nonsense. They wanted to banish infinity from mathematics altogether.
But ignoring infinity wouldn't make it go away, would it?
Yeah.
Didn't Cantor's work have major implications for, like, our understanding of continuity?
Absolutely. It really forced mathematicians to rethink the very nature of continuity, something we take for granted when we think about space and time.
It's like every time we think we finally got a handle on numbers, we discover something new, and it totally changes our understanding. It makes you wonder if math is something we invented, or if we're just discovering truths that exist independently of us, like out there in the universe, somewhere.
That's a big question. It's one that philosophers and mathematicians have debated for centuries.
I kind of lean towards the idea that math is a language that we've invented to describe patterns. And those patterns, they probably exist whether we're here to observe them or not. But the way we represent those patterns with numbers and equations and all that, that's a human creation.
That's a common view. And even if math is ultimately a human construct, it's amazing how effective it is, right? I mean, it really helps us understand and predict how the universe works.
Totally. Danzig actually makes this really cool analogy. He says, mathematicians are like designers who are creating these garments, but they don't know what creatures they might fit.
Oh, okay. I like where this is going.
And then sometimes along comes this shape that fits perfectly. And we're all like surprised and delighted.
That's such a great analogy. It's like, oh my gosh, it fits. Who knew?
Exactly. Think
Yeah.
about complex numbers, right?
Mhm.
At first they were just this strange imaginary thing, but then bam, they turned out to be absolutely essential for understanding things like electromagnetism and quantum mechanics.
It makes you wonder, right? What other seemingly unreal mathematical concepts are out there, just waiting to be discovered and applied to unlock the secrets of the universe?
Right, like what crazy new math might be the key to some major scientific breakthrough in the future? Something to think about.
Absolutely. And, we've really only scratched the surface here, this deep dive into Danzig's book. It's just a starting point. There's so much more to explore in the world of numbers.
Well said. And folks, the journey of mathematical discovery never really ends. Keep exploring, keep questioning, and who knows what you might find. Thanks for joining us on the deep dive.
It couldn't be expressed as a fraction at all, no matter how hard they tried.
So they were stuck.
They were stuck. It's what we now call the square root of 2.
Oh, the square root of 2.
Our first irrational number.
First irrational number, huh? That's kind of poetic when you think about it.
It is. So, they could get close with fractions,
I
They
could-
could approximate it.
But never quite get it exactly right.
Never exactly right. And Danzig, he actually explains how they proved this, using this really clever argument.
What kind of argument?
It's called proof by contradiction. Have you heard of that?
Proof by contradiction.
Yeah.
Yeah, that rings a bell. It's been a while, though, so remind me how that works.
Okay, so basically, you start by assuming the opposite of what you're trying to prove.
So in this case, like, you'd assume that the square root of 2 can be expressed as a fraction.
Right. But not just any fraction. It has to be, in its simplest form.
Reduced all the way down, can't be simplified any further.
Exactly. And then you go through these, steps,
Yeah.
totally logical steps, and you end up with
With what?
a contradiction,
Uh-huh. Which means
which means your initial assumption that it can be a fraction, well, it has to be wrong.
exactly. So the square root of 2 cannot be expressed as a fraction, period.
Yeah, mic drop. Okay, so proof by contradiction. That's like a mathematical puzzle,
It is, kind of.
but like a puzzle where the pieces, they just refuse to fit together no matter how hard you try. Exactly. And what's even cooler? This whole discovery, it opened up this massive new world of numbers.
A whole new world.
A whole new world beyond what we can easily express or understand with those nice, neat fractions.
So it wasn't just irrational numbers that were causing trouble for, like, the ancient view of
Right.
math. I mean, there were other things, too, weren't there?
Oh, yeah, definitely. There was a lot of stuff that was shaking things up back then.
Like what?
Well, for one thing, Danzig talks about these things called Zeno's paradoxes.
Zeno's paradoxes. Okay, yeah, those are definitely, like, mind-bending stuff. Those are the ones
Yeah.
that deal with, like, motion
Right.
and infinity.
Right. Those are the thought experiments, really.
Yeah, those are the ones that always make my head spin a little bit. Can you remind me of one?
Sure. So probably one of the most famous ones is it's about Achilles and the tortoise.
Achilles. Okay, now that's a name I recognize.
Right, Achilles, the fastest runner ever. Right. So the story goes, he's in this race with a tortoise.
A tortoise. That seems like a bit of an unfair matchup.
Right. But to make things, more interesting, he gives the tortoise this head start.
Okay, I see where this is going. So then what happens?
Well, what Zeno argues is that Achilles, even though he's super fast, he can never actually overtake the tortoise.
Whoa, wait, really? Why not?
Because by the time Achilles reaches the spot where the tortoise started, the tortoise has moved a little bit further ahead, right?
Okay, yeah, that makes sense.
And so this just keeps happening over and over again.
It's like a never-ending cycle.
Exactly. Achilles is always closing the gap, but he can never quite catch up.
It's like this infinite game of catch-up that's so trippy.
Right. And it all plays with this idea of like infinite divisibility. Like, can we ever truly reach a destination if you just keep dividing the distance into like smaller and smaller segments?
I mean, it seems like we do reach destinations in the real world, right?
We do, but that's the paradox, isn't it? These
Yeah.
things really stumped philosophers and mathematicians for a long, long time.
So, did we ever, like, figure it out? Did we find a way to tame infinity, mathematically speaking?
We did eventually. Over time, mathematicians developed all sorts of tools and concepts that helped them deal with infinity in a more rigorous way.
Like, what kind of tools?
Well, one really important one is this concept of limits. Have you heard of limits?
Yeah, vaguely. I took calculus, like, a million years ago.
Limits, that's a big part of calculus.
Mhm.
Basically, it's a way of like approaching infinity without actually getting there.
I see. It's like you're getting closer and closer and closer, but you never actually touch it.
Exactly. And then you have like the development of calculus itself, which completely revolutionized mathematics.
Yeah, calculus was a game changer. It's all about, like, change and motion and stuff, right?
Yep. And a lot of it relies on like these infinite processes, things like infinite series and infinitesimal quantities.
So we found ways to, like, work with something that we can never fully grasp.
It's pretty incredible, isn't it?
It is. Okay, so how did all of this, like, impact our understanding of the number system itself? I mean, I know we talked about natural numbers, fractions, irrational numbers. Where do we go from there?
Well, all of that led us to what we now call the realm of real numbers.
Real numbers. Okay, so that's like the big leagues of numbers, right?
You could say that. Think of it as like this massive expansion of the familiar number line.
Okay, let's break it down. Where do we even start with this number line?
Well, you start with the basics, right? The natural numbers, 1, 2, 3, and so on.
Counting numbers. That's easy enough. What's next?
Then you add 0, which, as we talked about earlier, was a big deal.
Right, 0. Huge turning point.
Then came fractions, and then we got those negative numbers, which really threw people for a loop back in the day.
Yeah, the idea of less than nothing must have been really hard to grasp at first.
It was. But we got there eventually, and all of those fit pretty neatly onto a number line, right? No problem there.
But then we have those pesky irrational numbers. And they don't really play nicely with the whole fraction game, do they? And, like, where do they even go in the number line?
Yeah, that's a good question. How do you even define them rigorously? I mean, they're kind of slippery, aren't they?
They are.
But don't worry, mathematicians are clever. They came up with some really ingenious ways to handle those unspeakable numbers.
Like what? What did they come up with?
Well, Danzig talks about this one concept called Dedekind cuts. Have you ever heard of those?
Dedekind cuts. Not ringing any bells. Sounds kind of, I don't know, maybe a little violent?
Maybe a little. Okay, so try to picture this. You're cutting a line into two parts.
Okay, I'm picturing it. The line cut into two parts. What's that got to do with irrational numbers?
Well, a Dedekind cut is basically a way of defining a number, any number, by how it divides all the rational numbers into those two sets. You've got all the rationals on one side of the cut and all the other rationals on the other side.
Okay, I think I see. So instead of defining the number by its, like, actual value, you're defining it by where it creates a boundary.
You got it. It's a bit more abstract, I know, but it's a way to include those irrational numbers in a more rigorous way.
So they have a place to live on the number line, even though we can't write them down as a nice, neat fraction?
Exactly. No more outcasts on the number line. Everyone's welcome.
It's funny how we keep having to, like, invent new ways of thinking about numbers as we learn more about them. It's like our concept of number is always evolving.
It really is.
But I have a question about those Dedekind cuts. Isn't the whole idea of a cut still kind of reliant on, like, geometry? I mean, we're talking about cutting a line, right?
Yeah.
But I thought we were trying to move away from our visual intuition about numbers towards a more abstract logical system.
That's a good point. And it's true that Dedekind used that, like, visual analogy to explain his idea, but the concept itself, the concept of a cut, it's not really about physical space. It's about logic. It's about how we order and divide sets.
Okay, that makes sense. So what exactly did Dedekind accomplish with these cuts? What problem did they solve?
Well, Dedekind's cuts, they helped mathematicians to construct what we call the arithmetic continuum.
The arithmetic continuum. Okay, now that sounds pretty impressive. What is that?
Think of it like this. It's a complete and unbroken number line.
Unbroken, so no more gaps.
No more gaps. It includes all the real numbers, rational and irrational.
So we finally filled in all those little gaps on the number line, huh?
We did, or at least that's what we thought at the time.
Uh-oh. I know that tone. What happened? Did we find some new gaps?
Well, you know how it is with math. Just when you think you've got everything figured out, something new comes along to blow your mind.
So those irrational numbers, they weren't the end of the story.
Not even close. We were about to enter a whole new realm of numbers, a realm that was even weirder and more mind-boggling than anything we'd encountered before.
Okay, you got to tell me more. What kind of numbers are we talking about here?
We're talking about those crazy entities that involve the square root of -1. We're talking about complex numbers.
Complex numbers. Okay, yeah, I've heard of those. But they always seemed kind of, I don't know, mystical to me, like imaginary numbers.
Imaginary is right. But as Danzig points out, what starts out as a mathematical fiction can often end up having some very real and practical applications.
Okay, I'm intrigued. Tell me more. How did these complex numbers even come about?
Well, it all started with the need to solve equations that didn't seem to have any solutions in the real number system.
Okay, that makes sense. Like, what kind of equations are we talking about?
Sure. Take the equation x squared plus 1 equals 0.
X squared plus 1 equals 0. Let me think about that one for a second.
Take your time.
Okay, so if you square any real number, it's always going to be positive, right?
Right.
So there's no way you can add 1 to it and get 0.
Exactly. There's no real number solution to that equation.
So what did mathematicians do? Did they just give up and say, well, this equation's impossible?
Nope. They're not the kind to give up easily. Instead, they did something pretty bold.
What did they do?
They invented a new number.
They invented a number.
They did. They said, okay, let's introduce this new number, this imaginary unit. We'll call it the square root of -1, and we'll represent it with the letter I.
The square root of -1. Okay, yeah, that's definitely a mind bender right there.
It is. But think about it. If I is the square root of -1, then I squared. Well, that equals -1.
Which means you can actually solve that equation we were talking about. X squared plus 1 equals 0.
Exactly. You get a solution in the complex number system.
Okay, so they invented this new number, this imaginary unit I. But how do you just introduce something like that into a system that's supposed to be based on logic and reason? I mean, it kind of seems like cheating, doesn't it?
Yeah, it does seem a bit strange at first.
Yeah.
And trust me, there were plenty of mathematicians back then who were super skeptical about these complex numbers.
They were probably like, you can't just make up numbers.
Right. It seemed like a bit too much of a stretch.
So how did these complex numbers eventually become accepted? Because, I mean, they're a pretty fundamental part of math these days, right?
Well, the thing is, mathematicians were able to show that these complex numbers, they weren't just some, arbitrary invention. They actually followed all the rules of arithmetic. You could add them, subtract them, multiply them, divide them, and they behaved in a consistent and logical way.
So they fit into the existing system, even though they seemed so strange at first.
Exactly.
But okay, even if they follow the rules, it's still pretty hard to wrap your head around the idea of the square root of -1. I mean, how did they make that concept more, palatable?
Well, they came up with a really clever way to visualize these complex numbers.
Okay, tell me they're about to bring in, a graph or something, because my brain needs some visual aid here.
You read my mind. They did bring in a graph. It's called the Argand plane. Remember that from high school math class?
The Argand plane. Yeah, vaguely. I'm getting some flashbacks to, plotting points and stuff.
That's exactly what it is. It's basically a two-dimensional plane where each point represents a complex number.
Okay, break that down for me. How does a point represent a complex number?
So the horizontal axis, that represents the real part of the number, and the vertical axis, that represents the imaginary part.
Oh, I see. So you're not just plotting, X and Y coordinates. You're actually representing the real and imaginary components of a complex number.
Exactly. And this, geometric interpretation, it was huge. It made complex numbers way more legitimate, It showed that they weren't just these abstract symbols floating around in some, mathematical void. They had a visual counterpart.
So you could actually see them, on a graph. You
Yeah.
could work with them geometrically.
Exactly. And this visual representation, it really helped people to understand and accept these complex numbers, which at first seemed so strange and imaginary.
I love that. It's like they took this really abstract concept and gave it a concrete form.
They did. And the truly mind-blowing thing is that this concept, this thing that started out as a way to solve certain equations, it ended up having all these amazing applications in all sorts of fields. Like they weren't just a mathematical curiosity, they were actually useful.
It's crazy to think that something that seems so, like, made up could have such a profound impact on the real world.
It really is.
So what kind of applications are we talking about here?
Well, complex numbers, they're fundamental to all sorts of things like physics, engineering, signal processing, you name it.
It's amazing to think that it all started with, like, this one weird question.
Hmm.
What's the square root of -1?
It really is. And it just goes to show that in math, you never know where a question will lead you.
It's like a journey of discovery, isn't it? And the
Yeah.
journey never really ends.
Exactly. And as Danzig keeps reminding us throughout his book, those boundaries of what we consider to be a number, well, they're constantly expanding.
We're always pushing the limits of what we think is possible.
Exactly. And, we're still on that journey today. There's so much more to discover about the world of numbers, so many more questions to ask.
It's a pretty exciting thought, right?
It is.
I mean, who knows what amazing new mathematical concepts are out there just waiting to be discovered?
Right. And who knows what those discoveries might lead to? What kind of breakthroughs might be possible if we keep pushing the boundaries of our understanding?
It's a good thing to keep in mind. The adventure never really ends.
Never. And Danzig talks about, this really fascinating idea, the work of Georg Cantor. Have you heard of him?
Georg Cantor. That name rings a bell. I think I might have come across his work in, like, a philosophy class or something. Didn't he do something with, like, infinity?
He did. He really shook things up in the world of math by developing a way to compare the power of different infinite sets.
Wait a minute, hold on. You're telling me some infinities are bigger than others? That sounds like a total paradox.
I know, right? It's one of those things that just seems completely counterintuitive. Like, how can one infinity be bigger than another? I mean, they're both infinite.
Exactly, that's what I'm thinking. So how does this even work? How do you compare infinities?
Well, it comes down to this idea of how we match up elements between sets.
Matching up elements.
Yeah, so with finite sets, it's easy. We just count how many elements are in each set, right?
Yeah, that makes sense. But what about infinite sets? You can't really count the elements, can you?
You can't. So instead of counting, we use this concept of one-to-one correspondence.
One-to-one correspondence. Okay, remind me what that means.
So basically, if you can pair up every single element in one set with a unique element in another set, then we say those two sets have the same size, or what we call cardinality.
Okay, so if you can create that perfect matching element for element, that means they're the same size, even if they're infinite.
Exactly.
But what happens if you can't make those pairings?
Yeah.
What if there are, like, some elements left over?
Then things get really interesting because that means one set is actually bigger than the other.
Wait, even if they're both infinite?
Even then. And Cantor, he was able to prove that you can't create a one-to-one correspondence between, say, the set of all natural numbers and the set of all real numbers.
So the real numbers are a bigger infinity than the natural numbers.
Exactly. It's like there are always going to be some real numbers left over, no matter how hard you try to pair them up with the natural numbers.
Wow. So you're telling me there are, like, different levels of infinity? That's a real mind bender. Did this change, like, how we think about the number line?
Oh, yeah, definitely. It led to a whole new area of math called transfinite arithmetic, which is all about dealing with these different levels of infinity. But I'll warn you, it can get pretty complicated.
I bet. So wait, didn't someone come up with, like, a paradox related to infinity?
They did. Actually, there are a few paradoxes related to infinity, which isn't surprising when you think about how mind-boggling the whole concept is.
So what's one of the famous ones?
Well, one of the most famous is Russell's paradox. It deals with sets that contain themselves.
A set containing itself.
Oh.
Okay, now I'm really lost.
Yeah, it's a tough one. Think about this. The set of all things that are not apples.
The set of all things that are not apples.
Oh.
Okay, so that would include, like, oranges, cars, clouds.
Right. And it would actually include the set itself, because the set itself isn't an apple.
Okay, that makes sense. The set is a thing, but it's not an apple, so it's a member of the set.
Exactly. But now things get a little tricky. What about the set of all sets that do not contain themselves?
Okay, the set of all sets that do not contain themselves. Got it. So does that set contain itself? That seems like a trick question.
It is a trick question. Because if it does contain itself, then it shouldn't be in the set, right? Because the set is defined as containing only sets that don't contain themselves.
Okay, yeah. So if it contains itself, then it violates its own definition.
Exactly. But on the other hand, if it doesn't contain itself, then it should be in the set, right? because it would then fit the definition of a set that doesn't contain itself.
Whoa. So it's like a self-contradictory loop. If it does, then it shouldn't. But if it doesn't, then it should. That's a real head-scratcher.
It is, it's a paradox, and it shows how even our most fundamental concepts, like sets and numbers, can lead to these incredibly complex and, well, paradoxical questions.
So Cantor's work, the whole thing with these different levels of infinity, must cause quite a stir in the math world, right? It's a pretty radical idea.
Oh, yeah, it definitely sparked a lot of debate. Some mathematicians, they loved it, thought it was brilliant, groundbreaking stuff. But others, they were not so happy about it.
Like, what were their objections? Why were they unhappy?
Well, some mathematicians, like a guy named Kronecker, they were really vehemently opposed to Cantor's ideas about infinity. They thought the whole concept was just too much, too messy, too abstract, too weird. They wanted to banish infinity from mathematics altogether.
Banish infinity. That seems a bit extreme, doesn't it?
It does. I mean, you can't just ignore something just because it's weird or challenging. It's still there, whether you like it or not.
Right. It's like sticking your fingers in your ears and yelling, la, 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 I can't hear you.
Exactly. But, Cantor's work, it didn't just cause controversy, it also had some really profound implications for our understanding of, like, some pretty fundamental concepts in math, like continuity, for example.
Continuity. Okay, remind me what that means again.
So continuity, it's basically this idea that, like, there are no gaps or holes in something. Like, think about a line. We usually think of a line as being perfectly continuous, right? No breaks, no jumps.
Okay, yeah, that makes sense.
But Cantor's work, with his different levels of infinity, it forced mathematicians to really grapple with, like, what continuity even means.
I see. It's like maybe it's not as simple as we thought it was.
Exactly. It raised all sorts of new questions about, like, the very fabric of the number line, the nature of space and time.
So this whole journey that we've been on, starting with those ancient counting systems and ending up with these like mind-bending concepts like infinity and complex numbers, it really makes you wonder, doesn't it? Like, what is math? Where did it come from? Did we invent it? Or are we just discovering truths that are already out there, waiting to be found?
That's a big question. And honestly, I don't think anyone has a definitive answer. It's something that philosophers and mathematicians have been debating for centuries. Is math like a human invention? Or is it a reflection of some deeper reality?
I kind of tend to think of it as like math is a language, a language that we use to describe patterns and relationships that we observe in the world. And those patterns, they probably exist whether we're here to observe them or not, but the way we describe them, the symbols we use, the equations we write, that's all human stuff. That's our invention.
That's a pretty common viewpoint. And even if math is ultimately like a human construct,
Yeah.
it's still remarkable how effective it is, right? It really helps us to understand and predict how the universe works.
It does. And Danzig makes this really interesting comparison. He says mathematicians are like, you know, designers who are creating garments without knowing what creatures they might fit.
Okay, I like that.
And sometimes along comes a shape that fits perfectly. And we're all surprised and delighted. Like, oh my gosh, it fits. Who knew?
That's a perfect way to put it. It's like those aha moments in math when suddenly everything clicks into place.
Exactly. Like, think about complex numbers. At first, they were just this strange imaginary thing, but then, bam, they turn out to be essential for understanding things like electromagnetism and quantum mechanics.
It makes you wonder, right? What other seemingly unreal mathematical concepts might be out there just waiting to be discovered and, like, put to work in the real world?
Right. What crazy new math might be the key to like some major scientific breakthrough in the future? Something to think about.
It is. And, we've really only just scratched the surface here, this whole deep dive into Danzig's book. It's really just a starting point. There's so much more to explore when it comes to the world of numbers.
It's a pretty vast world, that's for sure.
It is. And it's a world that's full of surprises and wonders and mysteries.
Well said. And for all you listeners out there, remember, the journey of mathematical discovery, it never really ends. Keep exploring, keep questioning, and who knows what you might find.
Exactly. Stay curious.
Thanks for joining us on the Deep Dive.
It's a journey that takes us to some pretty wild places, like the realm of infinity, and even with all our fancy math tools, and concepts, infinity remains this challenging concept to, like, really wrap our heads around.
It does, doesn't it? It's like you can talk about it, you can use it in equations,
Mhm.
but can you ever really, like, grasp it? I'm not so sure.
It's a tough one for sure. And, Danzig, he highlights the work of this mathematician, Georg Cantor. He really shook things up.
Georg Cantor, okay, yeah, that name rings a bell. Didn't he have something to do with, like, different sizes of infinity?
He did. He developed this whole way of like comparing the power of different infinite sets.
So are you saying some infinities are bigger than others? I mean, that sounds like a
Yeah.
total paradox.
I know, right? It seems completely counterintuitive. But Cantor actually proved that, like the set of all natural numbers, 1, 2, 3, and so on.
Yeah, the ID numbers.
Right. That set is actually smaller than the set of all real numbers, like all the numbers on the number line.
Hold on. How can one infinity be smaller than another? I mean, they're both infinite.
I know. It seems crazy. But it all comes down to how we, like, match up elements between sets.
Okay, matching up elements. So, like, with finite sets, it's easy, right? We just count how many elements are in each set, and we can see which one is bigger.
Exactly.
But with infinite sets, you can't really count the elements, can you? It's like they go on forever.
They do. So instead of counting, we use this idea of one-to-one correspondence.
One-to-one correspondence. Okay, remind me how that works.
So basically, if you can pair up every single element in one set with a unique element in another set, then we say those two sets have the same size, or what we call a cardinality.
Okay, I get that. It's like a perfect matching game.
It is.
But what happens if you can't make those pairings? Like, what if there are some elements left over in one of the sets?
Well, then that's when things get really interesting, because that means that one set is actually bigger than the other.
Even if they're both infinite.
Even then. And what Cantor showed was that you can't create this, like, perfect one-to-one correspondence between the natural numbers, 1, 2, 3, and so on, and the real numbers, which include all those irrational numbers and everything in between.
So there are always going to be some real numbers left over, no matter how hard you try to pair them up with the natural numbers.
Exactly. It's like trying to, I don't know, fit all the sand on a beach into a thimble.
Okay, yeah, I see what you mean.
Yeah.
There's just, like, more stuff in the set of real numbers. So you're telling me there are different levels of infinity.
There are.
That's wild. Did this discovery, like, change how mathematicians thought about the number line?
Oh, absolutely. It opened up this whole new area of math called transfinite arithmetic.
Transfinite arithmetic. That sounds intense.
It is. It's all about, like, dealing with these different levels of infinity. But be warned, it can get pretty complicated.
I bet. It's making my brain hurt just thinking about it. So wait a minute. Didn't someone come up with, like, a paradox related to this whole infinity thing?
They did. In fact, there are a few paradoxes related to infinity.
Well, yeah, it's infinity, right? It's bound to lead to some paradoxes.
Exactly. But one of the most famous ones is called Russell's paradox. It deals with sets that contain themselves.
Sets that contain themselves. Okay, now I'm really confused.
Yeah, it's a tricky one. Think about the set of all things that are not apples.
Okay, so that would include, like, oranges, bananas, cars, clouds.
Right, all kinds of things. But it would also include the set itself, because the set itself, it's not an apple.
Okay, I think I get that. It's like the set is a thing, but it's not an apple, so it fits the definition.
Right. But now, here comes the tricky part. What about the set of all sets that do not contain themselves?
Okay, the set of all sets that do not contain themselves. So the question is, does that set contain itself?
Exactly. It's a bit of a mind bender, isn't it? Because if it does contain itself, then it shouldn't be in the set, right? Because the set is only supposed to contain sets that don't contain themselves.
Right, so it would violate its own definition.
But then if it doesn't contain itself, then it should be in the set.
Because it would then fit the definition. Whoa, it's like this weird circular logic thing. If it does, then it shouldn't. But if it doesn't, then it should. That's a paradox for sure.
It is. It's a paradox.
Yeah.
And it just goes to show how even our most basic concepts, like sets and numbers, they can lead to these, like, really complex and mind-bending questions.
They really can. So Cantor's work with these different levels of infinity and all that, it must really shaken things up in the world of mathematics, right?
Oh, it did. It was definitely controversial. Some mathematicians, they were totally on board. They loved it, thought it was brilliant, groundbreaking stuff. But others, not so much.
What were they so upset about?
Well, some mathematicians, like a guy named Kronecker, they were vehemently opposed to Cantor's whole thing with infinity. They thought it was just too abstract, too weird, too messy.
Too weird. Come on, that's part of what makes math fun.
I know, right? But for some people, it was just a step too far. They wanted to, like, banish infinity from mathematics altogether.
Banish infinity. That's like trying to banish the ocean. It's not going to work.
Exactly. But, even though it was controversial, Cantor's work had a huge impact. It forced mathematicians to really think about some pretty fundamental concepts in a whole new way, like continuity, for example.
Okay, that's another one of those words that sounds kind of I don't know, philosophical. What does it even mean in math?
So continuity, it's basically this idea that there are no gaps or holes in something. Like, think about a line. We usually picture a line as being perfectly continuous, right? No breaks, no jumps.
Okay, yeah, that makes sense.
But Cantor's work with these different sizes of infinity, it really challenged that intuitive idea of continuity.
It's like, maybe it's not as simple as we thought.
Exactly. It led to all sorts of questions about the nature of the number line, the nature of space and time. It was a real game changer.
It's amazing how these seemingly simple questions about numbers can lead to such, like, profound and mind-blowing ideas.
It really is. It's one of the things I love about math.
Me too. So, we've come to the end of our deep dive into Danzig's book. We've explored the history of numbers, from those ancient counting systems to these incredible concepts like infinity, complex numbers, and beyond.
It's been quite a journey.
It has. And I think it's safe to say that we've only just scratched the surface. There's so much more to learn and explore when it comes to the world of mathematics.
Absolutely. And the best part is the journey of discovery, it never really ends.
It doesn't. And I think that's a good takeaway for our listeners. Keep exploring, keep asking questions, keep pushing the boundaries of what you think is possible.
Stay curious. That's what it's all about.
Well said. Thanks for joining us on the Deep Dive, everyone. We'll see you next time.